body for giving continuous measurements. The most well-known biosensor is the glucose sensor, which measures the concentration of glucose in the blood or in the skin. This is very helpful for patients with diabetes. With a biosensor, patients and doctors immediately get the information they need in order to optimize treatment, reduce unnecessary hospital visits, and enable self-management of health and disease. A biosensor consists of 4 major components: a molecular recognition process, a signal generation process, a disposable sensor device, and a reader instrument. Recognition molecules in the biosensor bind to the biomarkers. The recognition molecules are, for example, aptamers, enzymes, or antibodies. The molecular recognition leads to a signal, for example, an optical, electronic, or magnetic signal. All this happens inside a disposable sensor device, where the molecules come together. Finally, the reader instrument measures the signal and translates it into information that is meaningful for the user. There are many diseases and many biomarkers, each having different measurement requirements. Also, there are many technological ways how a biosensor can be designed. That's why Census was founded, the annual international student competition.
Yeah, so this is the things actually I taught last week. So this is the very important for the development of device for detection of the disease biomarkers. So let's come some new topic today. I hope many people shall join here. Yeah. So let's think about what are the challenges of the biosensor, right? So we are going to develop some sensing device, but why we will develop sensor device? And let's find out the challenges and the problem we are trying to solve. So see, that's why this point comes the lab on a chip. What is the lab on a chip technique? I mean, where the whole lab work. I mean, see, as I told you last time, in last class, come to here. Yeah. So generally in the laboratory, so when we are sending the samples, so the main drawbacks in the laboratory that is the very laborious process. We are handling a very large volume of the sample, and it's very time consuming and very complex steps we are following, where trained personnel, they are handling the samples. See, so these things generally people are well trained person, they're doing in the lab. So in the lab setting, many steps you have to follow. Sample processing, you have to handle very carefully, and very well trained person only they can do, right? So if these all the steps, this is called in the lab environment steps. If all the steps can be done in a single chip, if this can be done in a single chip, see. So here is some pictures of the chip like this one, or like this one, where all the lab work. See here, generally the well-trained person, they're doing in the bench, they're doing many lab work like sample processing, then adding the reagent, incubating the sample. So for that, sometimes it takes a long time, and we need so many chemicals also. We have to handle very carefully. So this is all the lab work generally people are doing, but we can do all the steps, all the lab work steps inside the chip. I mean, you can see here some small chamber. So we can add some reagent here like these chambers, or we can integrate some channel. See here, some channel already there. So we can integrate some channel with this chamber, so that the reagent can go through this channel. It will come to the maybe reaction side. So reaction will happen here. So it will be some automated. Means if you if you inject the sample, or if you drop the sample, and so sample will come here. So reagent, it will dissolve the reagent. It will go through the channel. It will come to the reaction side. So like this, all the lab work systems can be done automatically on the chips systems. So this concept is called lab on a chip. That's why, because on chip all the lab work will be done automatically. I mean, no need any extra step by outside on the outside the chip. Everything done on the chip. Also, we don't need any trained person because we don't need any special handling, because we just drop the sample and we'll wait, because the reaction everything will be done on the chip. And finally, we will integrate this chip with some electronic device, and we will apply some potential or some electric field or electron or some electronic potential, I mean electrical potential, something like this. Then signal will be, I mean data will transfer to the electronic device, and you can see the digital value, how much biomarker present. So this is the concept of the lab on a chip. There is so many steps, like here you can see I shown here, like sample purification, sample injection, sample mixing, sample amplification, sample detection, sample separation, everything that can be done on the chip. Okay, guys, is it clear? So why lab on a chip is important and why it is called lab on a chip? Okay, students, or can
Yes, sir.
can I
Yes,
repeat?
no, sir.
Huh?
No.
Okay, very good. See, so here actually we shown the all the steps. See, sample purification means sometimes we need to purify the sample. Something, think about the like blood sample, right? So blood sample contain lots of blood cell, but we need only the plasma, maybe, right? We need only plasma. Plasma means, do you know the definition of the plasma or the serum? Plasma serum means the in the blood there is a lots of blood cell and other liquid part. So that liquid part is called the plasma or the serum. So that plasma or serum maybe we need to separate. So that's, we need some purification that can be done also on the chip. So how we can do that, I will teach you slowly one by one. And sample injection, sample mixing. Maybe we need this sample mixing with some reagent. So what we will do? Maybe here we can inject the sample. Here we can inject the reagent. So they all come to this channel, and there is some mixer. This is called microfluidic mixture here. So when they will go through this channel, they will mix together properly. So this can be done on the chip. So sample mixing, then sample amplification. So how we can amplify? Maybe we can, sometimes we need some temperature. Maybe this sample can react with this reagent around maybe 90°C or 75°C, something like this. So maybe we can apply some heat. So how we can apply some heat? So around this microfluidic channel, maybe we can put some coil, some electrical coil, something like, or some wire we can put in, and we can apply some current, something like this, so that we can generate some heat. So that heat can be supplied to the sample, and that can amplify the signal. So that signal, that is called the some amplification technique. So that also can be done. Then detection means there will be some detection area where maybe you can add some actual like working electrode, counter electrode, reference electrode that I mentioned, the electrochemical procedure. I mean some electrode you can add here. So by the help of that electrode, you can detect how much biomarker present. So that is called the detection area. So that also can be done. So this everything can be done. So this is the very simple example that I mentioned already in the last class, like glucometer, Payne's test. So this is kind of the lab on a chip. So everything will be done on the single chip. No need any extra steps. So people, I mean the layman, they don't know about much things about this device, but they can handle it at least. They can handle it. So this is the main challenges we can solve by the lab on a chip. So now think about what is the impact of this chip. So why we are thinking about on this, I mean why are we giving more importance on this lab on a chip? Why? So first of things, the unique advantage of this lab on a chip is the miniaturization. Why? Because we can develop a very small lab, I mean very simple, very small chip. So no need, we no need to depend on bulk instrument. So because of the miniaturization, we can bring this one close to the patient. I mean, this is very useful for point of care. So miniaturization is the important key factor for point of care device development, and lab on a chip will help you this miniaturization. Okay, and second step is the low reagent volume. Low reagent value. Sometimes we are using many reagents for the signal amplification on lab on a chip, but the reagents are very expensive. But on the lab on a chip, we can use very small amount because we need very small volume sample also. So you can, if you see in the lab on a chip, because of the small size, only few microliter, like 10 or 10 to or 5 to 10 microliter, only very small amount sample we can inject, and we can detect everything by using very small volume. That's why we need also very low reagent. So it will, that's why although reagents are expensive, but because of low volume or low reagent volume, we can decrease. I mean, we can make a cost-effective device, and we decrease the price. So this is the important things for the development of a lab on a chip. And another thing, the rapid analysis. So because of the automatic systems and just you can drop the samples, it will go through all the channels and reagent can be mixed automatically. So that's why we can make the systems very rapid. and uh, and early detections. Why the early detection? Because of the signal amplification strategy we can use here, and we can detect the biomarker at the early stage. And automation that I already mentioned, and portability. So because of the smaller size, so it is very useful for portable biosensor device development. Okay, okay, it's clear the advantages of the lab on a chip. Okay, students, it's fine.
Yes,
Hello.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good, good. See now see the indicative application. See, sometime we should ask the questions to you. If we not interact, maybe you also will sleep, and I will not get the the energy to teach you, right? So we will interact sometime, and we will ask the questions also during the teaching time. Okay, now see the indicative applications. What is the main application of this lab on a chip? Diagnosis. So point of care, this term is very important for the device development, and lab on a chip will help you to develop these things. Second thing, detect some environmental the hazards, like maybe you want to go for field testing, like in the field you want to detect some like arsenic or lead in the drinking water, so you want to go to the river water side, or you want to detect some nitrate, phosphate in the soil sample, or you want to detect maybe some pesticide. So you should you have to visit to the field for the field testing. So you should bring your device near field, right? So for that environmental monitoring, your device should be portable and handy, and lab on a chip will definitely help you for development something like this environmental monitoring device. Okay. Another thing, defense and security. The defense and security means sometimes we are for security purpose or for the defense purpose, we are developing so many devices that can detect the biomolecule from your like what do you mean, from your saliva sample or from breath samples. Or sometimes, say, the traffic police, they are detecting alcohol by using some sensor, or you can develop some sensor that can detect some like lung disease or something like this from your breath sample. So that kind of things you can develop easily. You can think about from how you can, because when you're breathing, so some biomarker also can also emitting. So from that some volatile biomarker, so you can detect that volatile biomarker also, and that is very much useful for the defense and security purpose. So we can use that kind of sensor device. And food safety, we are storing in our shopping mall, not I mean in this food store area, long times. Maybe they are spoiled, maybe they're poisonous sometime. They're so how we can check them that food are healthy or not? So for that purpose, we can use some very simple sensor. Just we can dip inside the food, or we can maybe take some liquid samples from the food, or whatever, and we can check food quality, or regenerative medicine, chemical synthesis, drug screening. So everywhere we can use this kind of lab on a chip concept. So as I mentioned last time that a lab on a LOC means lab on a chip. So LOC has a huge market right now. So if you are interested in this area, I mean you are doing a very good work, because nowadays lab on a chip market is huge, and huge amount of money. It's in many company industry they are investing. So if you can develop something like prototype, something like this, any prototype, if you can develop, and if you want to start a startup or something like this, definitely you will get a good job, or not only like this, you are actually serving your society, and you will get very good fund. I can assure you, because nowadays people are actually looking for a very simple handheld device that can be useful for common people. And yeah, so that I think the startup, something like this, you can start if you have some prototype. Okay, now I will show you a very simple and very informative video where you can see that just I taught you these steps, like as I mentioned here, like sample purification, simple injections, sample separation, detections, like that can be done on lab on a chip. So here is a very good video. Let's enjoy this video. You can see how all the steps can be done on a single chip, and this is automatic. So let's see one by one steps. And actually upper part, actually the mechanism of the reactions, everything is going on. And the lower one picture, you can see this is actually the chip device. Here you can see where this reaction actually happened. Let's see. And there is no sound, just video. See, this is the chip. This is like a very simple handy chip, and this is the inside view. There is a inlet, nanostructure pores. So you can see, if you see the here actually dropping just a drop of blood sample you can drop. Now you want to separate the blood cells, right? So there is a separation chamber. Yeah, this is the nanopore side. You can see here blood cells are separating, but biomarker that actually you want to detect, you can see they are going through this pore size. This is kind of filtering process, right? Now you see, so here we are separating some channel, right? 1, 2, 3, some channel we can make on the chip. So, and on that channel, actually you can immobilize some antibody. This Y-shape size is the antibody. So antibody are the bioreceptor. So they can accept your biomarker. I mean, that can adsorb on the surface because of the antibody antigen binding. And specific biomarker, I mean here 1, 2, 3. So 3 chamber, you can put 3 different antibody. So at the same time, they can detect then 3 different biomarker because they are very specific for antigen. So if you antibody 1, here antibody 2, and here antibody 3, it means so you can detect 3 different antigen at the same time. And they can adsorb on these 3 different detection site. Let's see. So now see these 3 different antibody, they actually adsorb by 3 different antigen. Now in the detection side, you can see one. So at the beginning, so what happened? So there is 3 different antibody. So there only 3 different antigen they adsorb because of the specific antigen antibody binding. Now this antibody and antigen, this complex now can adsorb on the sensor surface by the help of another antibody. That is also specific for their antigen. So this 1, 2, 3 channel, you can see only the second antigen cannot bind in this left side because this antibody only specific for this antigen. So this one bound, and you can see this the upper one, the upper antibody. It is you can see the shiny one. This is kind of some enzymes or nanoparticle. So we can conjugate the antibody with some nanoparticles or enzyme. So why? Because nanoparticles or enzyme they will help for signal amplification. So why we need signal amplification? This thing that I will teach you slowly. So this is kind of the mechanism, the reaction mechanism, or the what I mean, how a lab on a chip actually can work for these diagnosis. That is actually showing. See, all the biomarker they are going out. You can see here, all the other biomarker they are not absorbing on the surface. See, they are going out. Only the specific one, they are actually absorbing on the surface. And excess, see, if your sensor surface becomes saturated with the antigen, then the excess one, they also will go out. They will not absorb on the surface. Then they finally they will come close to the detection area. I mean, this is the final site detection area. They will come there, and then we can apply some electrical potential or something like this. Then electrochemical reaction will happen here, and we can measure the number of the electron by the in the form of current or in the form of charge, something like this. Okay, students, is it clear?
Sir, I did not get like how enzyme works, like here how it is working, and which is the enzyme like in this video.
Yeah. See, in this video, you can see I'm showing you again. So you can design this circle, this one. This one can be enzyme or this one can be nanoparticle. So why we need enzyme or nanoparticle? Because this nanoparticle enzyme actually directly will participate in some chemical reaction. That chemical reaction actually will amplify the signal to background ratio. That actually I will teach you. That I will teach you very clearly. Just I am giving you some basic picture first here. Then I will correlate this reaction mechanism with some chemical reaction and conjugation chemistry, everything I will teach you. Okay. But just because it's a very beginning and very, early stage to teach you this one. Just I'm telling you that we have to conjugate some antibody with some nanoparticle or with some enzyme, and they will help you for some reaction. And that reaction or chemical reaction will help you to generate more, I can say, some electron. That electron we can measure in the form of current or in the form of charge. Basically, you are getting higher signal.
Sir,
But
is it because like this enzyme has more active sites of where the biomarkers uh, can get attached
no, no.
compared to
No. It
this.
is something like different. Enzyme actually, it is behave like a catalyst. So it will catalyze some reaction. If you have some enzymes or some nanoparticle on your surface, then and when you are adding some chemical, so that chemical will react with the enzyme or the chemical will react with the nanoparticle, and they will amplify the signal. So something like as a catalyst, they will react. They will act. So that thing I will teach you later. Okay.
Okay, sir.
Okay, yeah. Uh, okay, that's all. Then go to the next slide. Okay, so now this kind of lab on a chip concept now we can use that just I mentioned for the different kind of disease diagnosis. Here one point I mentioned bench to bedside diagnosis. So what is the meaning of bench to bedside? Bench that I mentioned, bench means laboratory, bedside means near patient. So whatever we will develop in our laboratory, so we will bring near the patient or near the patient side. That is called bedside. So So what's the current available solution for diabetes? So we have to develop something, some sensor device that can be useful near the patient. That is called the bedside application. Like some portable glucometer we can develop, right? Some portable glucometer that can detect the glucose near the patient. Let's see what's the current solution for the diabetic patient. There one solution available right now in the market that is very low cost, I mean cost effective, and but the problem is that it is invasive. Now come to the point, what's the definition of invasive and what is the definition of non-invasive? So invasive means if we need to prick your finger, I mean it's sometimes something like painful technique. I mean if you are using the blood samples, then you have to prick your finger, right? So this is that kind of sample is called invasive sample, because it is painful also, because we need the syringe, needle, these things, right? So you can see the technique for glucose detections. Just we have, first of all you have to prick the finger, then take the drop of the blood, then use that drop of the blood, just you can touch your finger near the chip, then this chip now will start that all the reaction mechanism, everything that just I showed you in the video, and it will show you the digital value of the glucose present in the blood sample, right? But this is because of the invasive technique we cannot use for diabetic patient. It is not recommended also, because every time before the meal patients should check their glucose level, and if he or she needs to prick his or her finger almost before the meal, it is very painful, or it is not very, not comfortable for him or her. So that's why scientists are looking for some non-invasive technique. Non-invasive means just you can, like a band-aid type things, you can attach on your skin, or you can wear like a smartwatch. So it can detect the glucose level from your, maybe from your sweat sample, or from your interstitial fluid or something like this. So that is non-invasive sample. Non-invasive means no need to prick your finger, no need blood samples, but it can detect the biomarker from your non-invasive samples, like saliva samples, like sweat samples, like urine samples, something like this. They are non-invasive. But main drawback for the non-invasive technique, the devices that are available in the market right now, they are highly expensive. That is the main drawback. Like if you want to buy this kind of the smartwatch, it was almost very expensive. It's at around 150 to 200 pounds the value of the smartwatch. So it is not affordable. I mean, common people, they cannot use always this kind of devices. So we have a area that we can explore in our near future in our research. So we have to find out some solution. Means it should be non-invasive, at the same time it should be cheap. I mean not expensive, like disposable, you can use and throw, something like this. But at the same time it should be non-invasive. So basically I will show you one problems here. I mean, first see why we need the glucose for continuous monitoring, and how we can solve this by using some non-invasive technique. And by using some non-invasive technique, we can monitor the glucose level in our body fluid. So what kind of body fluid? So one example of the body fluid is the sweat sample or interstitial fluid. What is the interstitial fluid? Means just, I mean, yes, if under your, I mean the skin, then if you go just below the skin, you will find some body fluid. That body fluid is called interstitial fluid, and this interstitial fluid also contain many biomarker, and that biomarker also, if you can detect, you can say the level of, I mean the disease level, you can predict. So you no need to detect, no need to go for the blood sample, but you can go for maybe interstitial fluid. But that interstitial fluid we can collect, or it can be absorbed on the device in non-invasive way. Means no need to prick your finger skin. See one video here. So they mention how we can continuously monitor the glucose in non-invasive way.
What is continuous glucose monitoring? You may be wondering, what is continuous glucose monitoring, or CGM? In the next couple of minutes, we will explain what CGM is and what it can do for you. We will also introduce you to the various parts of the Guardian Connect system and let you know what you can expect when using CGM. Your glucose value constantly changes, going up and down depending on many factors such as food, insulin, and exercise. And up until now, you have used your blood glucose meter to tell you what your glucose value is. However, your meter can only tell you what your glucose is for that moment. What if there was another way to get information about your glucose levels? Well, CGM gives you a way to see what your glucose levels are throughout the day and night. The CGM system is made up of 3 parts: the sensor, a transmitter, and a monitor. The sensor is inserted under the skin, so it is in contact with the fluid between your cells.
See here, you can see just when a sensor actually attached on the screen, actually your nervous system, I mean, why you feel pain? Because you have a lot of your nervous system is affected by the needle or by the syringe. Then that's why it become painful. But just under the screen, there that fluid is here. There's an interstitial fluid available, but it will not damage your nervous system, everything. So that's why you will not feel any pain. Just you can attach here one sensor. Maybe it contains very small needle that is called micro needle. So when it attaches on the skin, so this micro needle will be inserted to thus under the skin here, some sample there, that is interstitial fluid. So it will absorb to the sensor. It will not come to your nervous system. So it will not damage these things. That's why you will not feel any pain.
Called interstitial fluid. The transmitter is connected to the sensor. The sensor then measures the glucose in the interstitial fluid and sends this information to the transmitter. The transmitter then wirelessly sends this data out to your device. Glucose is always moving between the blood and interstitial fluid. BG meters measure glucose levels in the blood, and sensors measure glucose levels in the interstitial fluid. This is why meter readings and glucose readings from your sensor will rarely be exactly the same. This difference between BG and SG is okay and should be expected.
Yeah, that's what I'm saying. Here, actually, we have to now compare the glucose level in your blood sample and the interstitial fluid. So and then only we can say, yeah, so if the blood glucose level and the interstitial fluid glucose level that you are getting, and if we can correlate them, yeah, if interstitial fluid level glucose is this much, and then it is corresponding to that much glucose in the blood samples. We have to correlate definitely, because blood sample glucose is the standard one. That is the actual glucose you have to predict by your sensor device. So when you are getting the glucose value in the interstitial fluid, at the same time you have to compare it. And such like this, so you have to calibrate your sensor. And finally, you can bring that sensor device in the market. Before calibration, you always have to compare the level with your blood samples. That is the things you have to keep in mind.
Let's see how a roller coaster can help illustrate this. Picture your blood glucose and sensor glucose as cars on a roller coaster. The front car will be your BG, and the back car will be your sensor glucose, or SG. As the roller coaster starts up the hill, you can see that the BG in the front car is leading the SG in the back car, and the numbers are different. As the cars head down the hill, or as glucose is trending down, you can see the numbers are still different. Most often, the BG and SG numbers will be close to each other. However, you'll see a greater difference in BG and SG on the bigger hills, or when glucose is changing more rapidly. For example, after food, after insulin, and after exercise. When you use CGM, the focus is not on the individual number, but on the trends, since your glucose constantly changes. Is your glucose rising slowly, or is it falling rapidly? Your CGM system can alert you on your high and low glucose values and show you the speed and direction that your glucose levels are moving, giving you time to take action if needed. Keep in mind, CGM does not replace BG meter readings. BG readings are still needed to keep your CGM system working properly. It is also necessary to confirm your sensor glucose with a BG reading before making any treatment decisions, such as giving insulin for a high BG or treating a low. CGM is a tool that can give you insight to how your glucose levels change throughout the day and night. Expect that it will take a little while before you feel comfortable with this technology and know how to use the information you're receiving.
Okay, so yeah, so here now, so after this lab on a chip, now I will going to show you one more component, a similar like lab on a chip, but where we can use this technique on printed circuit board. Okay, so hello students. So is it fine? Everything fine?
Yes, sir.
So some more. So continuously,
Yes, sir.
continuously I'm giving you more input, more information, and just try to understand them. Then I will go for some specific application or specific side where I will give you more. I mean, very detailed side. Just now I'm throwing some keywords. What is this? What is that? So some keywords you should know these things before going the very deep knowledge, before going to the very deep idea on biosensor. Now see, just think about the lab on a PCB. Now I taught you lab on a chip. Now here I'm teaching you lab on PCB. PCB is printed circuit board. I think the electronics student, many of you are here in this class. You are very much familiar with the printed circuit board, right? So what is this printed circuit board and how we can use this one for, for biosensor development? And there is many advantages if we use the printed circuit board for biosensor. And lab on a chip integration is our main focus. So we always trying to develop some lab on a chip, and that should be integrated. I mean, say we are developing some chip, right? So that maybe contain some electrode, some working counter reference that I taught you last time, and that chip should be integrated with your some portable device like a smartphone. So it should be integrated. So it should be integrated with your device, right? Hello students, just 1 minute. I'm receiving one call from our institute. Just 1 minute. I'm coming back. Okay, students, let's start again. See, so lab on a PCB is nothing. Hello, you can hear me, right, students? Hello?
Yes, sir.
Yes, sir.
Here, the PCB printed circuit board. Now we are going to use. So why? See, you can see here some images of PCB, and I think you are very much familiar with this kind of the printed circuit board. See, like the computer, or I think sometimes you are playing with different kind of like this. Sometimes you're breaking your device and you are checking, what is this kind of this wire and this point, these things, like you are playing from your childhood, right? So many of you know very well these things. So if this kind of this PCB boards, they're very, very cheap. And India, everywhere you can find many industries, they are making this kind of the printed circuit board. We have very well established industry we have. So if the base system is easily available, then easily you can minimize the cost, right? So what we'll do, on the base system of this printed circuit board, we can fabricate our biosensor. So how we can fabricate? So here is the one picture in the right hand side, you can see. So this one, right hand side, you can see. Here, see, we can design definitely whatever you want. You can design on the printed circuit board. Anything, you can play around on this and you can design anything. So this is kind of the USB port you can design. Here you can design some channel like this. This is called the microfluidic channel. So this microfluidic channel actually necessary for mixing the sample, something like this, or heating the sample, that I already told you that we need for the lab on a chip case. So this microfluidic channel can be integrated easily on printed circuit board. Now come to the working side. So here in the right hand side, you can see you can develop some small area where you can fabricate your biomolecules. Like this small area, it is called WE, is the working electrode. This is working electrode. Then C means counter. This is counter electrode, and RE is the reference. This is reference electrode. So why we put these three electrode for biosensor design? That also I will teach you after a few classes. Then I will teach you then why we need 3 electrode system for biosensor, especially for the electrochemical biosensor. That I told you that we are interested electrochemical biosensor, right? That we are interested. So we can fabricate this kind of the electrode, like working electrode, reference electrode, counter electrode on the sensor chip. Now on the working electrode, so if we enlarge this one, working electrode, so we can immobilize many bioreceptor. So one bioreceptor is the antibody, for example. So I just keep the one bioreceptor always constant, that is antibody. There is so many bioreceptor like aptamer, DNA, RNA, everything can be used as a bioreceptor, but just for example, I'm thinking like antibody. So antibody you can immobilize, I mean you can attach antibody on the sensor. Antibody you can attach on the sensor surface. So by using some immobilization chemistry that I will also teach you later. So this working area that contain already antibody. Now if you drop the sample and if the sample contain antigen, then they will bind on the surface. And that sample actually you can inject here. That is called inlet. So on the inlet side, you can inject. So you can put here 1 or 2 inlet. So one side you can inject sample, and other side you can inject some reagent, basic chemicals that will help you for signal amplification, for some reaction that I told you last time, like enzymes and nanoparticles you can use, right? Okay. Now, when you will inject these two, then they will go through this channel, right? Then they will come to your working electrode side. And if this sample contain antigen, then they will bind. Now you can apply some on the back side. You can fabricate some electronic component where you can and by the help of that component, you can apply some potential. And also you can fabricate something like a wireless device also. So they can send the data wirelessly via Bluetooth. Via Bluetooth to your portable system like smartphone. So you will get the value on your smartphone screen. So something like this. So also not only the wireless system, maybe you can directly insert your chip by using this side. Like this is the USB, like USB port. By using this one, you can inject to your smartphone to the USB port. You can insert here, and you can apply some potential or something like this by using the app. So you can install some app on your smartphone, then you can apply some potential on this chip, and you will get the value how much biomarker present in your sample. Okay, students, is it clear? I can repeat otherwise. Hello, is it fine?
Yes, sir.
Okay, yeah. So see how many in the class right now, in the 45 students you are here. So I think many of you are not responding. So if you don't understand anything, maybe some of you are from maybe other department, maybe it is not clear for you, but you can ask me right now. You can ask me, I can clarify the any problem if you face anything. So don't hesitate, you can ask me. Or uh, so this is the time actually, because this is the very big, very early. This is the very early stage of this nanobiosensor class. So you should know all the points, all the keywords. Otherwise, you cannot understand the whole syllabus. Please keep asking the questions.
Sir, how good or efficient is an electrochemical sensor versus if we compare it with a chemical sensor?
Okay.
If I want to say identify protein conformations, then is electrochemical sensor an option over there?
See, chemical. You actually see chemical means there is some reaction, right? So maybe some that I mentioned, maybe some enzyme here, like you have some enzyme and you are using some substrate that are reacting with the enzyme, and you are getting some product. That is the chemical reaction, right?
Yes,
Right.
sir. Yes.
So this product, when this product form, so it always generating some electron. So that electron actually we are collecting by the help of electrochemical process. So basically they are related. So whatever in any chemical reaction you can measure by electrochemically. So they are actually related. They are not competitor to each other. They are actually they're very related. They're very much complementary to each other. If there is any reaction happen, then definitely there is some electron transfer process. That electron you can measure by electrochemical way. So any chemical reaction you can detect actually by electrochemical way. Okay, they're complementary to each other. They are not competitor. Okay.
Okay, sir.
So I will teach you many examples.
Okay.
Just try to understand each point, then slowly I will enter one by one all the points. I will teach you. See now, here you can see here one like small you can see this is the kind of needle. This is called the micro needle. So this micro needle actually very much useful for non-invasive diagnosis. So what we can do, this micro needle we can put on the sensor chip here, and we can put this needle on your screen like a band-aid things you can attach on your screen. So this needle actually can easily can be inserted on your skin, and it will not be painful because it will not harm your nervous system. Your nerve will not be affected. So that's why you will not feel any pain. Very small needle. Just you will insert the skin. Then the fluids that just under the skin, that is the interstitial fluid, that will be absorbed. So then that fluid then go through this channel and it will come to the sensor surface. It will come to the sensor surface. So, and many bioreceptor like antibody, everything will be immobilized here. So your biomarker or your target will be adsorbed on the working electrode, and then we can detect easily. And this is called a waste channel, waste chamber. I mean, the excess fluid will be stored here. So this is the concept on your whole chip. See here, I will show you one thing. That actually I by myself actually I developed one when I was in UK, University of Bath. There actually I tried to develop one sensor chip. So something like this, like Band-Aid. Huh? See, so this needle, this sensor, everything will be there. Then you just attach on the skin. So why I put the baby? I mean this baby here because many developed countries in this very early age, like they are within 1 year or 2 years age, they're also suffering from diabetes. But just think about at within a whole day, how many times you can prick their finger. Just to think about the baby's finger, how you can prick the whole day. 15 times, 20 times, is it possible before their meal? So that's why we have to think some alternative process. That is the non-invasive process. Something like this. So we can attach some device and they can absorb the body fluids and they can detect the glucose and send the data. So this is the one solution. Yeah, so here actually some picture that is lab on PCB that I mentioned. So this is kind of the printed circuit board. This is kind of the printed circuit board, or something like, I mean, anything you can think about, some different design. So here actually these two actually I designed by myself. This is some actually lab work I am showing you. Some lab work. This is some lab work actually I personally done. That actually going to show you here. So what we did, see here, 1, 2, 3, 4 channel, right? So on a single chip, actually I fabricated 4 channel. So this channel can be useful for maybe glucose detection. This channel can be useful for maybe some malaria detection. This channel can be useful for dengue, and this one can be detection for some cancer biomarker. So one chip can be useful for multiple analyte detection. So this is called multiplex biosensor. So this one I can say here, multiplex biosensor. So multiple analyte can be detected. Okay, on PCB. But here you can see in this multiple biosensor, there is no channel that is called microfluidic channel. So without microfluidic channel we can use, or with microfluidic channel. If necessary, we can integrate. Right. So here's a microfluidic channel. Now come to the point. Cell power. Why I put the cell power? Sometimes maybe without any external power, we can generate the power on the sensor device. That I mentioned here. You can see in this printed circuit board, one channel one point can be used as an anode, another point can be used as a cathode, and another one like reference. Why we need reference one? Actually, that actually help you with. Its potential will be always constant. Then we can measure the other potential, right? So that actually I will teach you again later. But just I'm showing you that we can generate a fuel cell on your biosensor chip. So fuel cell, or this is simply you can say biofuel cell. So biofuel cell you can develop on the sensor chip. Okay, so how? See here some picture here. Here actually we developed a anode, and another point we developed as a cathode. How we can use? See, anode maybe it can be gold, and cathode maybe it can be some platinum, some different materials you can use. Somehow their potential differ. We have to create some potential difference between two electrodes. Also, you can immobilize some biomolecules like some enzyme, and we can generate some potential difference between anode and cathode. By helping this potential difference, when you drop the samples, this sample come close to this electrode and they will react on the electrode and it will generate some potential difference. So this is called some biofuel cell. Just think about sorry, I'm giving you some example. Like here one anode. On anode, you can immobilize glucose oxidase, one enzyme. So this glucose oxidase can react with glucose. So glucose can react with glucose oxidase and it will form like gluconic, it will form gluconic acid, right? So during this reaction, it will release the electron and some potential will be generated. At the same time, another electrode you can fabricate here. Maybe you can here immobilize another enzyme, that is like bilirubin or something like this. Bilirubin oxidase, something like enzyme you can immobilize, where oxygen can react and it will develop another potential difference. So because of the two different reaction and two different potential, because of the potential difference, we can generate some power, some some power difference we can generate. That is the principle for the biofuel cells or some battery. Battery principle we can incorporate in the on the biosensor chip. Now, so if we can get some energy from this electrode, that energy can be useful for biomarker detections. Why? As I mentioned, come to here, as I mentioned, so it is the biosensor, right? So in the working electrode, you are immobilizing some antibody. Then if antigen come, it will bind to this antibody and you have to detect this antigen, right? Concentration of the antigen you have to detect. The biomarker concentration or your target concentration. So for that, you have to apply some potential that I mentioned. So for that, you need some external energy, external power. But that external power can be provided by this biofuel cell. And if this number one biosensor and number two biofuel cell, if we can integrate, then this biosensor become a self-powered biosensor. So one biosensor become the self-power if we can integrate some biofuel cell. So this here is the picture actually you can see here. Like this banded kind of things, one glucose biosensor. It can absorb the glucose from the body fluid cell, and that glucose actually reacting with the glucose oxidase, some enzyme on the sensor, and that is actually providing some energy difference on anode and cathode, and it will now generate the power difference. And that power actually we will get from that power, that self-power that biofuel cell. Then it will provide the energy. It will provide the energy to the biosensor. Then we'll get the biosensor data. That sensor data we can transfer wirelessly via Bluetooth to your mobile device. This is a simple, concept. Simple concept. So your sensor device, where if you think about this is the biosensor working electrode where antibody immobilized. If you have any biomarker, that you will bind for how much biomarker already there on your working electrode biosensor. For that you need some external energy to provide some power, potential that can be provided by the fuel cell. Also, Bluetooth technology you can use to transfer this value to your smartphone or something like portable electronic device. So this kind of biosensor is called self-powered biosensor device. And you can, continuously we can monitor the biomarker level. So this is kind of like a wearable sensor. So because you can put this on your screen and long time you can use this continuously. That's why that is called continuous monitoring of the biomarker by using this self-powered biosensor. Okay. So here I will show you some another application. See, this one actually also I personally developed some component when I was in the Michigan State University, USA. So actually, he is my actually supervisor at Michigan State University, USA. So where we actually developed some biosensor device. You can see in this one. This is a biosensor device. It is very small. You can see our this is the very SIM card, like a SIM card, very small one. I mean, we miniature as I mentioned, we can miniaturize it easily. You can see there is two inlet on a same sensor device. Two inlet. One portion you can inject some sample like blood. Another portion you can inject some chemical, and they will come through the mixer microfluidic channel, and then biosensor device. One biosensor device you can see the 3 channel. One is the working, one is counter, and another is the reference. Then this portion you can easily add with some electronic component. So this is the electronic component. So through your app, I mean one app you can install to your smartphone, and you can control how much potential you want to apply on this biosensor. So see, this is the actual biosensor, and this is the three connector. They are connected with this working reference counter electrode. Then you can control the applied potential, everything, by using this app. Then when you inject the sample in inlet 1, and when you inject your chemical in inlet 2, then everything will be mixed. It will come to the sensor surface, and reaction will happen on the sensor surface, and you will get the data to it will be visible on the skin. So like this way, actually, we detected malaria in the whole blood sample. We detected malaria in the blood sample. Actually, we visited University of Malawi, and there actually you can see this is the smartphone, and we integrated this, and see, we just drop the sample here, and we are trying to detect the malaria in the blood samples. We visited this University of Malawi, Africa. So this was very, very useful for point of care diagnosis. Now we are trying to commercialize this kind of device in the market. Okay, students, is it clear until here, until this stage?
Yes, sir. Sir, what is the material used?
Which material you are asking? This sensor, this device material?
Yeah, yes, sir. That means that transparent one is there now. That is glass or what?
Yeah,
something different.
Yeah, see, many people using many different kind of material. Like we tried PDMS, like some plastic.
Plastic.
Some flexible plastic material you can use. Also, as I mentioned, you can use any kind of PCB material also. Material also you can try, but that's depend actually. That is not. I mean, there is not gold standard that you have to use PDMS or PMMA, something like that. There is no gold standard. You can use anything, but it's depend on your sensor performance. If your sensor performance is good with the PDMS, let's go for PDMS. If it is not good, then leave it. You can go for another material, like any PC material also you can try.
Okay, sir.
Yeah. So this is actually last few years, like 2 years before, we published this work in some Nature journal, scientific report here. So this is, we developed very small. This is a very small chip like this. As I mentioned, I told you that we need 3 electrodes, integrated system like working, reference, counter electrode. And what is their role? Actually, I will teach you. Just remember, we need working, reference, 3 electrode system for electrochemical measurement. For electrochemical measurement, we need this. So on the working area, see, we immobilize the antibody for specific antibody. So here actually we detected malaria. So this malaria biomarker name is the PFHRP2. PFHRP2 is the malaria biomarker. So we did anti-PFHRP2, means malaria antibody. So here we immobilize the antibody. Now, when your blood, if you drop on the device your blood sample, so this blood sample will go through some membrane. And this membrane, you can keep in the dry form all the reagent. And you can add here some membrane that can help to separate the blood cells. That is called plasma separation membrane. Here actually we put a membrane that is plasma separation membrane. In the plasma separation membrane, it will help to separate all the blood cells. So you will get only plasma. So this plasma will contain your biomarker. I mean the malaria marker. Now, when this plasma liquid will go through this all the papers, and here already many other reagents will be in the dried condition or lyophilized condition. That's called. So they will dissolve. And also you can use other antibody or some other marker that can help to some sandwich assay formation on the working electrode. So maybe, I mean, your sensor surface, I mean, this is your sensor surface that already contain one antibody. And if the malaria marker there, then it will bind. And you can use some another antibody that is called a secondary antibody. So secondary antibody you can keep on the paper. So they will also come to the close to the surface and they will also bind. And this secondary antibody can be conjugated with some enzyme or with some nanoparticle. So why we need this enzyme nanoparticle? Actually, they will act as a catalyst. They will react with some chemical that is like something substrate, and it will form some product P, and it will release the electron. So that electron actually will measure with the help of this 3 electrode system. So that sandwich formation I will also teach you one by one classes. So yeah, this time this is also kind of lab on a chip. All the steps. So all the steps will be done on a single chip, and very less time we need for the detection, and almost within 5 minutes we can detect malaria biomarkers. This is very interesting thing. So something like very simple chip you can develop. See here we mentioned some like RuNH3 whole. So this is kind of the chemical methane blue, some chemical. So some chemical we can keep in the dry form here. Okay, this chemical will come to the surface as I mentioned. So we need some chemical, which one will react with some nanoparticle or with some enzyme, and it will give you more electron, and more electron means we will get the more signal. That's why we need some chemical. And antibody, they will actually help you to bind the antigen on the surface. And ascorbate oxidase, this is kind of some enzyme actually. This is some chemical also. This will help you to remove some interference species. So interference species means in the blood samples also contain some ascorbic acid like vitamin C. You know, our blood sample always contain vitamin C. This is high concentrations also. And that ascorbic acid are the interfering species actually. This interfering species can hamper your electrochemical measurement. So if your sample contains some extra species, you should remove them. So how you can remove? You can use some extra chemical or some extra potential you can apply. Somehow you have to remove, or you can use some filter. So that they will not interfere during your electrochemical measurement. Okay, guys. Clear? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
See, it is very innovative, interesting thing. You can think after maybe let's wait few more classes, just learn more. Maybe first 1 month, I think you will get so many idea first. Then I think after next month, I will arrange some classes where you can freely, you can give your idea. We can one by one we can discuss, because see, this is kind of very generic sensor. Now we can think about this kind of sensor for any kind of disease. So you can think about slowly. But just wait for a few more classes. You will get so many key points, keywords, more and some fundamental ideas you will get. Okay, now what is the future? So I taught you so many these things like sensor, PCB, lab on a chip. So what is the future perspective? Means, see, there is a. I just here make a table. One is portable bio device. This is the very big picture. I mean, the very good one you can think about. One is the portable biosensor device for early detection that you can use. Like you can develop some sensor that is wash free. Wash free means uh, you are developing some sensor and just dropping your sample. You have no need to wash your surface. Wash means some laboratory people in the laboratory, well-trained persons, when they are diagnosis your sample, blood sample, many times they are washing their systems. I mean the electrode anyhow, or any maybe 96 soil plate, everything. They are washing many times to form their sandwiches, say, or some any detection procedure they are following. They are washing many times. That's why it's time consuming. Also, we need the training. But if we can develop some washing free, then layman also can use. We can minimize the time, we can minimize the cost, and something like this. So this key point you should remember, we should develop a biosensor that is washing free. Okay. Another key point that we have future, that is a smartphone based platform. As I told, I think nowadays everyone you have the smartphone, right? So if any company, if they say today they developed a very small chip, it is very maybe within 100 rupees, and it can detect COVID-19. So definitely, what you will do, you can buy and you can easily. I mean, if it is integrated to your smartphone, you can integrate with the smartphone. You can detect COVID-19 in your home, right? Then company will get a huge market because smartphone already available everyone. That's why if you can develop any biosensor that can be easily integrated to the smartphone, then you will get a good future. Your research area will be very innovative, right? And in the printed, whatever you are developing any sense, anything, if it can be printable, like on screen, like you can think about, see, this is kind of wearable sensor. You can print the sensor on your screen and it can detect the glucose, uric acid from the sweat sample or from the interstitial fluid. So it should be printable. Also, same time, as I mentioned, this is wearable sensor. This is another future. Okay. And lab on a PCB. This point you should keep in mind. PCB has very big market because we have well established fabrication technology all over India. We have all over world. We have printed circuit board fabrication technology, and it is not expensive. That's why if you can develop any biosensor on PCB, easily you can minimize the cost. Okay, clear, guys?
Yes, sir.
Yes, sir.
Good. Now, fuel cell. Another things, you can integrate that I already taught you. If you integrate the biosensor with the fuel cell, then you can easily develop a cell power biosensor. Then no need to depend on the coin battery. Sometimes the battery they contain lead or any other, I mean, the pieces that is not environmental friendly. But if you can develop some biodegradable battery, and if you can integrate them to the biosensor, then that will be more innovative and more important for, I mean, it will be environmental friendly sensor, I mean, whole sensor. And somehow you developed a biosensor that is environmental friendly, but it's running with the battery. So the whole system you cannot throw easily, right? So, but if you can develop a biodegradable battery and that can give the power to the biosensor, then it is nice idea. You can integrate both together, means it become self or sensor device. These things you can think about. This kind of future. You asked me, I think, in the last classes. I mean, how you can think about in your research. How like there is so many research area available. You can try this one. You can try as a master project. In your masters also, you can think about some project in this area. Not only that, if you go for your PhD, that also you can think about some project. Also, if you go some industry or if you want to start a startup company, anything, you can think about on this area. Say, I like this word. See, this word I always saying to my students, we have to always keep in mind this one. Breakthrough discoveries cannot change the world if they do not leave the lab. I think you are agree with me. You will be agree. Breakthrough discovery, they cannot change the world if they do not leave the lab. So whatever you are trying, the portable system, everything, so try to commercialize them. So something like this you should develop that should come to the market. It is not like this we are publishing paper, we are getting more journals that will be useful for your PhD, for your postdoc, for the position, not like this. So we are trying to develop something device that should be useful for common people, and we can bring this one in the market. That is the utility, and that is the main concept of this coursework. This nanobiotechnology enabled point of care class, this is the main concept. I always will teach you this idea, how we can bring a device in the market easily. Okay, guys. Hello, students. Are you agree with me? This one.
Yes.
Sir.
Yes, sir.
Yes, sir.
Okay. I think yeah. The first few class I will go slowly. I will not give you so many key points, so that otherwise everything will be mixed up. And slowly I will give you some ideas. Then I will enter to the actual. I mean the details. And then one by one point I will teach you very detailed story, like why we need 3 electrode systems, how we can design sensor device, all the detailed idea now I will give you. First few classes is the basic idea. And you should learn all the keywords, these things. So I'll not go very fast, first few classes. I think that is fine for all of you. I think that's all for today's class. Next class I will share these slides with the Microsoft team. And now next class also I will share some ebook. So try to download that ebook that will be available in the e-material that I already create a channel. Just download it. Try to read some papers or some ebook. Okay.
Yes, sir.
Sir?
Yes, sir.
Okay. So guys,
Sir?
yeah. Tell me. You can ask question now.
Hello?
Yeah, you can ask question now.
Sir, you mentioned about the sandwiched malaria detection technique. So in that technique, there are 2 antibodies are there. One is IgM and one is IgG. So which one is the primary antibody and which one is the secondary antibody?
Okay, let's just a minute. I'll show you. Let's open this slide again. This one, right?
Yes, sir.
See, as you asked, because you have some preliminary knowledge, that's why you ask these questions. But yeah, I can answer you this time, but I will answer, but I will teach you again this kind of thing. Which one primary, which one secondary, why we need sandwich. This one I will teach you again when I will go the details teaching. So see, this one is the attached on the sensor surface. This is the IgM. This is actually we are called the this is called actually capture antibody. Capture antibody, or this is actually primary we are considering. When antigen will come, they will bind here. actually we put here only Y shape. Actually IgM they have the like this 1, 2, 3, 4, 5 like this. I think you know this one, right? IgM.
Yes.
So we put here a very simple structure like Y shape only. So IgM, this is the capture antibody, primary. Now we add another antibody. This is the secondary. So when antigen will bind with the primary capture antibody, the secondary antibody bind with this antigen, and we are trying this secondary antibody. I mean, we form this sandwich ELISA because this secondary antibody will help you to generate higher signal to background ratio. That's why. But then when I will teach you signal to background ratio, that time I will teach you again. Okay.
Yes. Sure, sir. Yes.
Okay. Okay.
Yes.
Nice.
Thank you, sir.
Nice. Thank you. So,
Thank you, sir.
okay, I think if you want any more ideas and anything, because just this is the beginning of this course, if you need more ideas or more discussion, or if you want to improve the teaching something different way, you can freely discuss in this class. Okay.
Yes, sir.
Okay. I took attendance for all of you. 46, 45 students are here. Yeah. So please try to be here always in the class during the class time. Thank you, all of you. Next class, I will teach you some more ideas.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. See you. Thank you. Thank you.